years ago from having come eventually from a land very far away where everybody is a Canberra materialist and walks upside down and all kinds of different things. But she did her PhD at Otago, far away, even further away in New Zealand, and happily for us, drifted to this end of the world. And since then, she's been teaching at more places than I can remember, but ended up as before coming here as an assistant professor at Nottingham, where we are very pleased to have recruited her. She works, as you probably know, on all things Newtonian, that's to say all things to do with Newton and his surrounding sciences and scientists, and will talk to us today about this meeting is being recorded by, no, that's not the title.
Click got it, you'll be able to see the title.
Sorry?
Click got it.
Oh, got it, yes. It's definitely got Newton in it. Demonstrations, definitions, and Newton's experimental philosophy. So I'm looking forward very much to hearing that.
Thank you. Right. Okay, thank you for inviting me to come and speak. Okay, yeah, so I'm going to talk about this. So in Newton's Optics, in book 1, part 1, it opens with a list of definitions and then a list of axioms. And so you might expect from that Newton is going to then proceed by kind of giving us a proof method which will involve definitions and axioms, so a demonstrative method of proof. But we don't find that. As soon as he finishes his axioms, he finishes explaining his axioms, he tells us that he's going to proceed by a method that he calls proof by experiments. And that sort of seems a little bit surprising, a little bit dodgy for various reasons. And so what I'm going to do today is kind of talk you through what's going on here and hopefully hopefully convince you that the experiments do have some probative force and also explain maybe what the definitions and axioms are doing in that method. So what I'll do is first explain the demonstrative model of proof. Then I'll talk you through a very kind of simple case of Newton's proof by experiments. And then I will give you my take on definitions as what I term bridge rules. I guess I should stand over here, shouldn't I? Because you can't see the screen otherwise. It's warm. Okay, so let's start with the demonstrative model of proof. Okay, so in the early modern period, to prove something was just literally to make it known. There's nothing kind of fancy about what a proof is. It's just to prove something is to make it known. So in other words, to prove something is to make known, to prove is to make known the truth of something, to confirm a matter in whatever way. So this just comes from the Lexicon Philosophicum, so basically kind of the dictionary of philosophy from 1613. So that just kind of tells us what it means. So there were kind of lots of different proof methods that were kind of available, or at least there are different ways of talking about proof. But in the early modern period, demonstration was considered to be the gold standard of proof. So if we're talking about demonstration, then to demonstrate something was to prove it from necessarily true or self-evident principles by deductively valid rules of inference. This demonstrative model of knowledge comes from Aristotle's posterior analytics, but it was believed to be perfectly exemplified by Euclid's Elements of Geometry. It's not clear whether it in fact was perfectly exemplified by Euclid's Elements, because what the early moderns were working with was Aristotle's kind of take on what Euclid was doing. So Aristotle had this demonstrative method of proof, and he basically just rewrote Euclid's Elements using his method of proof. And so this is the thing that was passed down to us. But because of all of this, geometry became the ideal science. So the ideal way of acquiring knowledge. And this became the thing that natural philosophers wanted to exemplify. They wanted to figure out how you could have that kind of proof in natural philosophy. So the experimental turn of the 17th century led to the decline of scholasticism. So scholasticism was the kind of Aristotelian Catholic hybrid worldview that became very popular in the universities of Europe, hence why it's known as scholasticism. So scholasticism was the thing that everyone was being taught in all of the universities across Europe, but in various scientific or natural philosophical societies, most prominently in Britain, they were starting to challenge these methods. And so they became interested in the new philosophy. So we see people like Descartes, who are kind of developing new philosophical methods. But in Britain, it was the experimental philosophy which got picked up. So they followed the methods of Francis Bacon. And this was kind of presented the main challenge to scholasticism. And so Aristotelian syllogism, so the main way of reasoning in philosophy, fell out of favor. But early modern natural philosophers still sought to cast physics in a demonstrative mold. So they were still very concerned with certainty and the way that we could use methods that would lead to certainty. And so most early modern natural philosophers, even experimental philosophers, agreed with the following claims: that mathematics is a bearer of certainty. So one can reason deductively from axioms to theorems without any loss of certainty. So here the idea is if you start from self-evident, necessarily true axioms, and you reason well, if you reason deductively, you should be able to arrive at certain theorems. They also believed that it was possible to reason deductively in natural philosophy. So you should be able to move from principles to propositions without epistemic loss. So the challenge, well, the thing that you needed to do was then to achieve certainty in natural philosophy by finding appropriate principles from which to begin. So you needed to start from certainly true principles and be able to reason from them to propositions. This was the challenge. So the problem here is, of course, that to achieve the kind of mathematical standard of certainty, which is what they were after in natural philosophy, in order to turn natural philosophy into science, those principles needed to be universal and self-evident or necessarily true. And well, this was a problem for everyone doing natural philosophy, but it was a problem in particular for early modern experimental philosophers. So experimental philosophers arrived at their principles after constructing natural histories. So a natural history for an experimental philosopher is a set of acquired observations and facts about the world. It's not just a kind of, we're not just working with kind of a naive Baconianism here. We're not just kind of working with a system where you just gather, I don't know, facts about everything and just then try and generalize or theorize from those facts. What you're doing is kind of starting with a set of really specific research questions, and you're carrying out experiments to kind of in response to those research questions, and then you sort of tabularize them and get your, you're kind of systematizing your observations and so on. And so you're supposed to, at the end up with a kind of a really complete system of observations and facts about a particular subject area. If you arrive at, if you have one of those, then you should be able to theorize from there. So this was in theory what you're supposed to do. But the problem with this is that principles are discovered towards the end of the process of inquiry rather than at the beginning. And so the principles are already kind of lacking a lot of the features that we need axioms to have if they're going to give us certainty, reliably give us certainty. So in particular, one of the problems is this, that natural histories reported on data gathered from concrete and particular experimental events. Now, Hume was still a fair way off, but even the 17th century natural philosophers kind of recognized, well, they didn't call it the problem of induction yet, but they recognized that there was a problem with reasoning from particulars to generals and maintaining that kind of certainty. So they already recognized that there was a problem here. what they tended to try and do was to kind of give their experimental reports a narrative or historical form. So this kind of led to, have I got a, yeah, no, I didn't have that one. So what tended to happen was that these experimental reports were designed to kind of carry a reader along with the reports themselves. It kind of gave rise to this notion of virtual witnessing. So what you needed to do was describe your experiments in such a way that your audience could kind of see the experiment in their mind's eye or something like this. And so that had a kind of a tendency to universalize the experience in some sense. It kind of tended to abstract it from particular cases, but it didn't quite take it far enough, because what we then lacked was the kind of, what we were doing was appealing to the reliability of a witness and that kind of, and so even though they kind of thought they could get to a universal, maybe, principle based on these kinds of experiments, they couldn't get the self-evidentness that they needed, because something is self-evident if it doesn't need to be demonstrated or it doesn't need to be observed or proved by anyone. And the kind of emphasis on witnessing and describing the experiments showed that these principles were things that kind of needed to be demonstrated in some way. So we had this problem. Right, we've also got a bunch of additional problems about reliability of witnesses and so on that for various reasons tended to get focused on in these experimental philosophy descriptions. And so, you know, the skill of the experimenter, their social standing, philosophical reputation, all these things sort of tend to come into this. And so they kind of recognized again that there were these problems of reliability to do with kind of arriving at experimental principles. For some reason, I have to keep on double clicking the clicker. So this was the situation that a young Newton found himself in when he was in Cambridge studying for his bachelor degree in the mid-1660s. So he was encountering scholasticism at the universities, but he had an indulgent professor who gave him Descartes' books to read, and then he started reading the philosophical transactions that was being published by the Royal Society and so on. And so he kind of encountered this system where he was already kind of suspicious of scholasticism and was encountering these new methods. And so he was one of the natural philosophers who needed to focus on this particular problem. How is it that you go from natural histories to the right kinds of principles? Okay, so here we arrive then at Newton's optics, which of course happened, he didn't publish this until 1704, so that was kind of quite a long time after his days at Cambridge. But what we have here is, this is what happens in book one, part one, that we've got. He starts with his definitions. In fact, you might be interested, if you can't read what the top says there. This bit here, he says, my design in this book is not to explain the properties of light by hypotheses, but to propose and prove them by reason and experiments, in order to which I shall premise the following definitions and axioms. So he doesn't pretend that he's going to do something kind of in a demonstrative method of proof. He always says that he's going to use experiments to do this, but he does kind of imply and suggest that definitions and axioms are going to do something. The problem is that when we start looking through the proof by experiments, he never ever refers to a definition or an axiom in any of his proofs. So if they're doing some work, they're doing something kind of tacit behind the scenes here. And so the guiding questions of this research are, first, how does the proof by experiments function as a proof? And then what roles do axioms and definitions play in the trajectory from experiment to proven theorem for Newton? Okay, so that was the demonstrative method of proof, a brief historical introduction, and now I'll move on to Newton's proof by experiments. Notice that I keep on talking about experiments in the plural. A lot of people tend to slip into talking about Newton's proof by experiment In every case where Newton performs this method of proof, there are always multiple experiments. And it seems like the experiments are supposed to work together to give you this proof. There's never kind of a single experiment that does it. Okay, so I'll start this section by giving you a quick rundown on Newton's theory of light and color so that you can kind of see what all of his readers kind of knew at the time when they were looking at this. So, and this is basically, this is what people kind of already knew. Most people had read his first optical paper where he explains this stuff. And I'll kind of just present you with the key propositions that he accepts, the key aspects of his theory of light and colors. So he starts with this proposition that white light is composed of rays of every refrangibility. So refrangibility is a made-up word. Newton made it up. It means, well, refrangibility is just the disposition of a ray of light to refract. And what we have here is we've got light coming in through a hole in a window shutter, so an aperture. So we've got sunlight coming in. It's projected through a prism and onto a screen. And what Newton noticed was that the light tended to, well, the first thing that he thought was that it elongated. So what you've got, if that light had just kind of passed straight through onto a screen, it would have been circular in shape. But what Newton encountered was a kind of elongated circle, an oblong. And so what he realized was that white light is composed of rays of every refrangibility. So each of these rays has a different disposition to refract. It refracts to a different degree, and so they separate out as they pass through the prism. He then argued that there's a one-to-one correspondence between refrangibility and spectral color. So if we send white light in through the prism, so sunlight is white light, what happens when the rays separate into their different refrangibilities is that they also separate into their different color groups. So all of the red light has a certain refrangibility, all the yellow light does, and so on. And so what we get is a spectrum of color. So since we've got these two propositions, or these two premises, white light is composed of rays of every refrangibility, and there's a one-to-one correspondence between refrangibility and spectral color, that led Newton to his conclusion that white light is composed of rays of every spectral color. He was able to kind of perform another experiment to kind of demonstrate this as well. The classic experiment is just to prove that you can put all the colors back together again and get white. So what Newton would do was to take a lens, a glass lens, and project the light back through the lens so it gathered at a focus, producing white light again. And yeah, so this is the account. So there's a lot of new stuff going on in this account of light. So one of the key things is that color. Most of Newton's contemporaries believed that white light is the kind of the pure homogeneous thing that we're dealing with, and that colors are produced by the light kind of going through the prism and being sort of disturbed in some way. And it was kind of the disturbances of the white light that would produce different colors. Whereas Newton kind of established that this wasn't the case, and that in fact if white light is the thing that's odd, white light is the compound of all the different colors. So that's probably as much as we need to know, because the first proposition that I'm going to look at in the optics, or the first proposition we see in the optics, is basically this one, that there's a one-to-one correspondence between refrangibility and spectral color. Okay, so let's look at the optics. So proposition 1, theorem 1 in book 1 tells us that lights which differ in color differ also in degrees of refrangibility. Here, Newton gives us some interesting experiments. They might be somewhat unsatisfying, because he then later on defends a very similar proposition where he gives us a much larger number of experiments. But I picked this one because it's really the simplest experiments that I can give you to kind of just illustrate this point. Okay, so the first experiment involves this. Newton takes a piece of white card. He colors half of it blue and half of it red. And then he takes a prism and looks through the prism at the piece of card. And what he notices is that when he tilts the prism kind of upwards, the blue part of the card kind of appears to be higher than the red part. And then when he tilts the prism down, the blue part appears to be lower than the red part. So he notices that the two parts are kind of moving as blocks, but moving in different directions. Okay, so his conclusion from this is the following. He writes, wherefore, in both cases, the light which comes from the blue half of the paper through the prism to the eye does, in like circumstances, suffer a greater refraction than the light which comes from the red half, and by consequence is more refrangible. So I think that's pretty straightforward. All he's saying is that lights, well, the lights which differ in color differ also in degrees of refrangibility. So yeah, I think there's not much else to say about that. So this is the first experiment, and so yeah, and all we've got is that it's extremely simple. It's the kind of experiment where, all right, and he draws it too. He gives us this illustration of the experiment. So of course, what we have here is the card, and we've got the kind of he kind of explains. He kind of describes what the numbers mean and so on, and so we've just kind of got this description. The card, the illustration kind of emphasizes where the observer is in this picture, because it's the observer's kind of response to this that's really important here. This isn't just kind of an experiment that can kind of happen on its own, where there can be kind of some result that you see later. The result is how it looks to you as the observer, and so on. Okay, so the second experiment, Newton takes the same piece of card and he wraps some black thread around it, some skinny black thread. And he then projects that, he then takes a lens, a glass lens, and he kind of he uses that lens to project that red card onto a white screen. He writes that he uses a candle to do this, to create an additional light source, because he needs to do something to kind of brighten up the card a little bit to get it to project onto the screen. There's a thing where I'm presenting these things in a very kind of stylized way, which is really clear what the result is, but if you've ever played around with this kind of experiment, it's really hard to get any kind of sharp appearances. I mean, even if we just look at this screen in front of us with the light shining on it, it's just like not as sharp as you see it. So you can imagine what it would be like to try and do this experiment, on a winter's day or something, in Newton's rooms. So anyway, so he's presenting he projects the card onto a screen, and what he does is he sort of takes the card and moves it forward and back. And so what he notices is that when he kind of brings the card further forward, the black thread is much sharper on the blue side. And when he moves it kind of further away, the black thread is much sharper on the red side. So it should be clear now what the black thread was doing in that experiment. The black thread was there to tell him when he had acquired like the sharpest image, when he had managed to get all the color into a focus, into one focal point. So this is what he's doing. Okay, and so again, what he's shown us here is that the light kind of refracts to different degrees, and so there's a one-to-one correspondence between the color and the refrangibility. So he writes, in like instances, wherefore of the blue and red upon the lens, the blue was refracted more by the lens than the red, so as to converge sooner by by 1.5 inches, and therefore is more refrangible. So the reason why Newton has used these two experiments, which look extremely similar, is that the first experiment shows us kind of the first experiment shows us kind of a colored body. So we've got light coming from a colored body that we're looking at directly. This experiment is supposed to show us kind of colored light. So the light's kind of illuminated, and it's the light that's colored as opposed to the body that's colored. And so this is why we've got these two separate experiments, and together they're giving us this conclusion. Right, and here's the experiment, and here's how he's drawn the experiment. Notice that in this one, we don't have an observation point. My guess is that the reason for this is just that it's way too complicated to try and stick an eye drawing. But yeah, it's a bit kind of striking that there's no kind of observer lined in that, put in that experiment, in that illustration. Okay, so then there's a scholium. There's a sort of a discussion after this. So in the discussion, Newton suggests some other variations on the experiments that he talks through. He kind of clarifies the lessons. One of the things that comes up is that he talks about the kind of the problems with kind of trying to carry out the experiments under these kinds of circumstances. We learn that the red and blue light, he doesn't think that the red and blue light are kind of perfectly isolated. So we're not just dealing with kind of a homogeneous body of red light and a homogeneous body of blue light, but we've got kind of other colors that are kind of muddying the water, making the experiment less vibrant than it would otherwise be, because we've got kind of probably sunlight coming in that's all the colors and so on. Right, and so this is what he has to say about that. He says, now from these experiments, it follows not that all the light of the blue is more refrangible than all the light of the red. For both lights are mixed of rays differently refrangible, so that in the red, there are some rays not less refrangible than those of the blue, and in the blue, there are some rays not more refrangible than those of the red. But these rays, in proportion to the whole light, are but few and serve to diminish the event of the experiment, but are not able to destroy it. Just click something there. And so the point here is that he's saying, well, look, he hasn't perfectly isolated this, but the experimental result sort of still tells us what we need to know, which is that red light has a different disposition to refract than blue light. And this seems to be consistent. And so it doesn't really matter if the actual experiment is kind of a bit messy. We can idealize away from that, and we can sort of, and the theory itself tells us that what will happen under the ideal circumstances. We also learn about the scope of these experiments. And so Newton tells us that these experiments are supposed to sort of just tell us about the colors of natural bodies and kind of colors that are reflecting from natural bodies and so on. And then later on, he's going to go on and tell us about other kinds of bodies and what happens when these are reflected and so on. Okay, so some preliminary comments about what's going on in these experiments. Well, this is not a demonstrative proof. I mean, I already kind of front-loaded that, but there are no definitions or axioms appealed to in this. There's no sort of, the only propositions we see is the kind of the main proposition that's being defended. There's no premises along the way. And in fact, some people have convincingly argued that if we were to try and capture this kind of experiment in premises, if we were to try and capture this kind of demonstration or this kind of proof in premises, we lose something along the way, because that's not what's going on here. Another thing to notice is that it's the experiments rather than the illustrations or descriptions of those experiments that are supposed to have the pervasive force here. That's supposed to be what's doing the proof work, not the experiment, not the illustrations of the experiments. So again, we can't kind of try and capture the proof in terms of premises and a conclusion or in any kind of syllogistic kind of form, because we'll lose something along the way. What's important here is the process of the experiment itself, is kind of seeing the light go in through the prism and come out the other side or whatever. So, and the third thing to kind of notice about these experiments is, again, something I kind of front-loaded, which is that it's the experiments that are taken together to form one proof of the theorem. And so again, it's not like Newton has given us sort of two proofs for the theorem. They seem to be working together in some way to give us that. Another thing to notice here is that the experiments take the form of a narrative. So when Newton describes the experiments, he talks about how he carried it out, and this is what he saw, and he kind of describes it in this kind of past tense way, where he describes how he moved the prism and the kind of difficulties he encountered when he carried out his experiments and so on. So it's a narrative that you're supposed to be able to kind of imagine carrying out. But even though it's a kind of a narrative where you're supposed to get this sense of doing this experiment on a particular day, the results are reported in idealized form. It's only in the scholium at the end that we realize that actually the results weren't as perfect as he's reported. And so this is right. And so there's a sense in which the experiments are being presented out of context, and so they're not being attached to particular circumstances, which I think kind of gives us scope for thinking about these things as kind of universal and abstract. So the discussion, Newton's discussion, lacks the usual appeals to the status of the witness, which is kind of interesting. This is usually what we come to expect in kind of Baconian experimental texts, is that there's usually discussion about the status of the witness. Newton doesn't appeal to the status of the witness, which again kind of supports this idea that the reader is supposed to be a virtual witness here. And so they're supposed to be able to kind of work through it on their own. The experiments are described in just enough detail that someone could conduct them for themselves. And they're in just enough detail that if you read them through, you can kind of grasp what he is telling you. But there are kind of crucial details that tend to be left out of these experiments, that it would require a person to go and do the experiment for themselves to kind of really grasp that experiment. So all of this tells us that the conclusions of these experiments aren't to be taken on the basis of testimony. We're not supposed to just take Newton's word for it. We're supposed to experience these experiments for ourselves. And it's carrying out that experiment for ourselves and seeing that result that is supposed to kind of compel us to accept the conclusion. That is the kind of, I think that is where the pervasive force of these experiments lie. It's in your experience of that experiment that kind of compels you to accept that conclusion. If you've carried out the experiment properly, or if you've properly understood the descriptions of the experiment such that you can, in your mind's eye or in reality, see how the light is moving, then there's no way you could disagree with that conclusion. I think this is how Newton thinks this is working. Okay, so now we'll move on to the third part. What definitions are doing in this proof? Axioms as well, but I think the definitions are kind of more interesting here. So Newton's optical work has geometrical foundations, but it doesn't follow the demonstration method of proof, as we know. So what's going on here is that geometrical axioms are assumed. So here we encounter a really interesting thing that Newton is doing in the optics, something that he's kind of doing that other people hadn't. So prior to Newton, there was geometrical optics and there was physical optics, but people didn't do both of them. So in geometrical optics, you're interested in, you're treating your rays of light as straight lines. You kind of assume that light is propagated instantaneously because that allows you to represent your lines geometrically. You can just draw them as lines. You don't have to kind of think about them as points moving through space or anything like that. And you can, and what you're interested in there is in properties of refraction and reflection and so on. If you're doing physical optics, you're treating your light physically, and what you're interested in is kind of the nature of that light, how it's moving through space, and it's going to be at that point that you start being interested in color. So what Newton does is he kind of combines the two of them in a really effective way. So he takes his geometrical axioms, and what he shows is that if we treat rays of light as mathematical lines, then we can study optical phenomena with mathematical precision. But what he does new is he shows us that we can treat color with mathematical precision as well. Okay, so here are the axioms. We don't need to read all of them. The key point is that these are just things that that kind of everyone who knew about geometrical optics would just agree with. So they're just things like, so the first one, he tells us that the angles of reflection and refraction lie in one and the same plane with the angle of incidence. So and this is just something that kind of everybody knows who's studying this kind of stuff, and this is why we can represent. This is why in those previous experiments Newton was able to kind of represent the passage of light kind of in a 2D form, because the light is all kind of traveling on one plane. And so he just takes us through the standard things that everyone knew. So the angle of reflection is equal to the angle of incidence, and so on. He also gives us a bunch of diagrams And again, I think the diagrams are kind of interesting here. Most of them, as you'll see, have an observer drawn into them because it's important to know where the observer is supposed to be standing in these experiments. That tells us where the incident light is and where the reflection is and where the refraction is and so on. And it shows us what the observer will see versus in fact what's going on, things like that. And so so what we have here is just a bunch of geometrical diagrams. These are just kind of, you know, lines on a graph. Okay, and after he's given us these axioms, this is what he says. He says, for what have generally been agreed on, I content myself to assume under the notion of principles in order to what I have further to write. So if there are any kind of axioms or, you know, principles in this system, it's these geometrical axioms. And these are supposed to be what we're reasoning from, except that that's not really what Newton's doing here. And he says, and these may suffice for an introduction to readers of quick wit and good understanding, not yet versed in optics, although those who are already acquainted with this science and have handled glasses will more readily apprehend what followeth. So again, what's really important to Newton here is not the axioms themselves. Sure, if you haven't done geometrical optics before, you definitely need to learn his axioms in order to do this. But what's going to be important is having done optical experiments yourself, having handled the glasses, having done the work. That's going to allow you to easily apprehend what follows, is how he puts it. It's what's going to, in my terminology, it's what's going to compel you to assent to his conclusions. So what do the definitions do in all of this? Well, here are the definitions. They're defining rays of, he tells us what a ray of light is. He defines what refrangibility of rays of light is, reflectability, what that means. He tells us which, you know, how to define angles of incidence and refraction and so on. Oops. So this first, he defines a ray of light. I've kind of messed up on the coloring here and made it impossible for you to read. But he tells us that by rays of light, I understand its least parts, and those as well successive in the same lines as contemporary in several lines. So he's kind of given us a notion of a ray of light as being just the least part of light. And so it's kind of striking here that he thinks that light can be broken down into parts. But a ray of light is supposed to be that least part of light. And so he's kind of left it open about whether he thinks that the ray of light can be divided in both directions. So the least part is going to be kind of both that way as well as that way. So so kind of length as well as breadth or something like that. And so this is what he thinks. But he explains to us why he defines it this way. He says, mathematicians usually consider the rays of light to be lines reaching from the luminous body to the body illuminated, and the refraction of those rays to be the bending or breaking of those lines in their passing out of one medium into another. And thus may rays and refractions be considered if light be propagated in an instant. But by an argument taken from the equations at the times of the eclipses of Jupiter's satellites, it seems that light is propagated in time, spending in its passage from the sun to us about 7 minutes of time. And therefore I have chosen to define rays and refractions in such general terms as may agree to light in both cases. So what he's doing here is his defining ray in a kind of as general a way as he can, such that you can use his definition to do geometrical optics, where you can treat your light as being propagated instantaneously, and you can do physical optics, where you can recognize that in fact light is traveling through time. It's traveling from Jupiter's moons to us in 7 minutes. And so that's what he's done. And he seems to be doing this with all the definitions here. Is that he's giving us definitions that allow us to connect up physical optics with geometrical optics, that allow us to kind of make sense of both of these things. We can translate one into another. He also gives us, these are also striking definitions, the last two. So definition 7, he writes, the light whose rays are all alike refrangible, I call simple, homogeneal, and similar. And that whose rays are some more refrangible than others, I call compound, heterogeneal, and dissimilar. And he's written, and number 8 is the colors of homogeneal lights, I call primary, homogeneal, and simple, and those of heterogeneal lights, heterogeneal, and compound. So what's striking here is that he actually, in his earlier optical work, he argues for these. These are propositions. But here in his optics, these are just definitions. He's just said, well, look, and what's going on here is that he thinks that that say yellow light, there can be two different kinds of yellow light. You can get simple homogeneal yellow light, and so this is going to be light that after it's been broken down, after it's been separated out, you've just got kind of light that just has its property yellow. But then he also thinks that you can create yellow light by mixing other light together, combining it together. And so he thinks that you can get kind of compound yellow light and you can get simple yellow light. And so he's distinguished between these two things. And so he's just given us these as definitions. And here's his commentary on that. He says, the former light I call homogeneal, not because I would affirm it so in all respects, but because the rays which agree in refrangibility agree at least in all those their other properties which I consider in the following discourse. So he's not trying to say that he's being very careful to not attribute more properties to light than he has evidence of. At the very least, he thinks that any given ray of light has properties of color. It'll be, say, yellow. It'll have refrangibility, so disposition to refract consistently to a certain degree, and it will have that same disposition to reflect. These are the only properties that he's kind of given so far in this, and these are the only ones that he kind of really thinks that he's ever really certain about. And he doesn't, and he's being very careful here to not say there's going to be other, like we shouldn't think that they're going to be homogeneal in all their other properties, because he doesn't know what other properties they have. So he's kind of giving us this kind of thin notion of what homogeneal light is and so on. He also writes, for these are always compounded, all right, when he's talking about the compound colors, he says, for these are always compounded of the colors of homogeneal lights, as will appear in the following discourse. So again, actually, I don't know why I put that quote there. I think it's just telling us that what he's aiming to do in this, in the kind of following experiments. Okay, so what does this leave us? Well, I think what's going on here is that the definitions provide a bridge between the geometrical optics and kind of experimental optics. It's the thing that kind of tells us how to interpret our experiments in terms of the geometrical axioms we've got. We might refer to this as construal. I think this is definitely the kind of the terminology that I think gets used in kind of the modeling literature more generally. So the idea is that the definitions tell us how to interpret the experiments as abstract geometrical shapes. They kind of connect up the axioms with the experiments themselves. It's really worth knowing, emphasizing that Newton was extremely careful in how he characterized the relationship between abstract geometry in the real world. And this kind of leaves us with a remarkably thin construal. So this is why I wanted to emphasize the point about the properties that he attributes to light. He doesn't attribute more properties than he needs to. So the definitions allow us to view the experiments as abstract geometrical figures rather than kind of concrete events. And I think this is the thing that gives them something close to universality, which in turn, I think, gives the experiments probative force. So I think that what happens is that, you carry out the experiment and the experiment kind of compels you to assent to the proposition, but you have to understand the geometrical axioms in order to kind of properly get that probative force from that experiment, from the experiment. So, and the definitions are the thing that's kind of connecting up those two things together. Okay, so just to kind of finish up, what have we learned about Newton's experimental philosophy in all of this? Because I gave you kind of this example of experiments and so on, but this is a really kind of particular case. Well, so remember where we started with this. I said Newton kind of inherited this problem of experimental philosophy. How are we supposed to kind of achieve certainty? How are we supposed to turn natural philosophy into a science? And in particular, in Newton's case, how are we supposed to turn optics into a science, into something where we can achieve certainty? And I said, what was recognized at the time was that we needed decent principles, natural philosophical principles. They needed to be universal and self-evident or necessarily true. And this is the problem that kind of Newton was working with. And so I think what's going on here is that I think Newton, what we see here is Newton rising to the challenge of experimental philosophy. He sees that there's this problem and he gives us a method of proof. One of the things I think that kind of muddies the water here is that he uses the language of definitions and axioms and yet doesn't provide us with demonstrative proof. And I think what's going on also is that in doing so, he has transformed the meaning of proof, definition, and axiom. I can tell you more about the kind of what an Aristotelian definition is supposed to look like, and I can assure you that Newton's definitions are not Aristotelian definitions. They're doing some other kind of work for him. But I think that this kind of twisting of the language fits with a really familiar pattern to me of what I've termed in other work Newton's rhetorical style. So Newton kind of takes well-known terms and he sort of twists the meaning of them, changes the meaning of them slightly to fit with his methodology. He does this with terms like mass as that's kind of probably the most famous example of it, but he also does it with terms like hypothesis, principle. Even the term principle kind of gets changed and shifted in his language. There's lots of these kinds of terms, and I think that there's kind of evidence here that proof, definition, and axiom are also terms that he's kind of twisted the meaning of. And so what he's kind of done is and my theory on this is that he takes these terms, he kind of performs this rhetorical twist as a way of kind of keeping his work kind of consistent with what everyone's expecting. So, you know, you open up a book on optics and you go, oh, I don't know about this. Axioms, I understand what axioms are. Oh, good, definitions. And so then you kind of get carried through, and then all of a sudden, before you know it, you've been convinced by his proofs, even though he hasn't done anything the way that he was supposed to. I think is kind of what's going on in the background here. Whether he was successful at this or not, I think is another question. Whether these experiments kind of do actually count as proofs. I think in a modern day sense they don't really. I don't think there's any kind of understanding of what a proof would be that actually fits with what Newton's doing here. But I think there's something really interesting going on, and I think we learned something about Newton's approach to experimental philosophy in looking at this case. And that's probably enough. So thank you.